All right. Good morning, everybody. Welcome back. So let me start this week with some important announcements. So first thing, we will not have in class assignment this coming Friday. Okay. So therefore, we will have a regular lecture on Friday. And there is online homework for chapter 3, part number 2, due on Thursday. Okay, so this is quite a long homework, so I would suggest you to start as soon as possible. And if you are running trouble to finish it before the deadline, let me know. Then I can give you an extension. Okay, so let me know in advance, then I can get the extension placed. Okay, so last thing we talked about last week was regarding reagent in excess. So the strategy here, when you have a chemical equation or a chemical reaction, and you want to determine the amount of reagents needed or products produced, first thing is to write the equation always. Verify if the equation is balanced or not. If it's not, balance the equation. Then you are going to determine the stoichiometric ratio using the stoichiometric coefficients. And once you got to this part here, the rest is basically simple proportions. Always verify if one of the reagents is in excess, and then identify the limiting reagent. And you're going to calculate the amount of product using the limiting reagent. Okay, so the chemical equation will give us the ratio always in mole. And remember that we can correlate the number of moles and mass using the molecular mass of the compound. Okay, always 1 mole of any molecule corresponds to the molecular mass of this molecule. And that's how we are going to correlate moles with molecular mass when it is needed. Okay, so today I would like to talk about percentage yield, and then we will move on to the next chapter. In an ideal world, all the reactants are converted into products. However, most of the reactions do not go all the way to the completion. The reagents are not 100% pure in most cases, and experimental errors by lab personnel contribute to the decrease of the amount of final product obtained. The yield of product produced in any chemical reaction is going to be equals to the mass obtained. So mass obtained is the mass you obtained in the real world, divided by the mass that is expected. And if we are talking about the yielding percentage, then we will multiply the ratio by 100. Okay, so the mass expected is going to be obtained from the chemical reaction and the stoichiometric coefficients. And we are always expected to obtain a 100% yield. The reaction goes all the way to the completion. And the mass obtained is the data that you collected in the lab or the data that was provided at some point during the question. So let's start here with a very simple example. So let me just switch to my other screen here really quick. Okay, so let's go back to the hot dog example. So we know that we need one bread to one sausage to produce one hot dog. So very simple reaction, 1 to 1 to 1. That's the stoichiometric ratio for all the components here. What is the yield if we start with 3 buns and get only 2 hot dogs at the end? Okay, so when we are dealing with yield, we always need to know first the mass that is expected. Again, the mass expected is the mass if the reaction proceeds in a perfect way and all the reagents are converted to products. So we can say here that the mass expected would be a 100% yield. So if we start with 3 buns, because the ratio is 1 to 1 to 1, the expected amount of hot dogs here would be 3 hot dogs. Okay, so this is what is expected. However, for some reason, the reaction was capable of producing only 2 hot dogs. And that is the mass obtained. Okay. Therefore, the yield for this situation would be the mass obtained, which is 2, divided by what was expected if the reaction proceeded in a perfect way. And we are going to multiply by 100 to express the result in percentage. So we would get here an yield of nearly 67%. Okay, yield does not have unit because you are dividing mass by mass. So that is the way that you are going to calculate the yield of a chemical reaction. Okay, so unfortunately, I don't have too much time here to give a lot of examples. So we are going to do some practice tomorrow during the discussion. So let me switch back to the PowerPoint screen. Okay, so here is a strategy that I like to follow to determine the yield of a product formed during a chemical reaction. So always start writing the equation. Verify if the equation is balanced or not. If it is not balanced, you must balance the equation. Third step is always to determine the stoichiometric ratio using the stoichiometric coefficients and understand that the stoichiometric coefficients will provide the ratio between reagents and products. The theoretical yield or the expected mass, you will consider that the reaction is 100% successful. Always verify if there is any reagent in excess. Then we are going to calculate the yield for the reaction. And always, always, always have in mind that we can correlate moles with mass using the molecular mass of the reagents or products involved in the reaction. Okay. So a final example here, we will go back to the water formation reaction. So hydrogen combined with oxygen produces water. Balancing this reaction, we know that we need 2 parts of hydrogen to 1 part of oxygen, and that will produce 2 parts of water. Okay, so the stoichiometric coefficients will give you the ratio always in mole. Okay, 2 moles of hydrogen reacts with 1 mole of oxygen, producing 2 moles of water. And with that, you can write a sort of a conversion factor, and then from there is a simple proportion. Okay, let's assume that we start in a given condition with 5 moles of oxygen, and at the end, for some reason that doesn't matter at this point, we only collected 3 moles of water. What would be the yield for this situation? Okay, so it's not hard, but it requires a lot of practice, okay, to master stoichiometry. So let's see this case that we have to handle here. So if we started with 5 moles of oxygen, first thing that you need to think about when you are solving this kind of problems is, okay, so if I start with 5 moles of oxygen, if the reaction proceeds in a perfect way, what would be the mass or the amount of water produced? Just simply look at the stoichiometric coefficients and they will tell you the proportion. Is 1 mole of oxygen produces 2 moles of water. See that from 1 to 2, you always double. If you start with 5, the double of 5 is 10. Okay, so 10 moles of water would be the amount expected if everything goes right. However, for some reason, we were just able to produce 3 moles of water. Therefore, this is the mass that was obtained. The yield is simply what you obtained, 3, divided by what you expected, 10, times 100 because we are talking about percentage. And that would give nearly an yield of 30% for this situation. Okay, so keep in mind that your yield can never be higher than 100%. Okay, so that's the cap for any sort of yield. You cannot produce things from nowhere. Okay. All right. So stoichiometry, to be honest, is not easy, but I'm pretty confident that you can do it. It will require a lot of training. It comes down to proportions. Always think about proportions. That will guide you to solve any kind of stoichiometry problems. Okay, very good. So with that, I will finish this chapter. Chapters 3.7 and 3.8 were not covered, and I think you are going to have the opportunity to cover that in the lab. And here, if you have time, I have some recommended exercises that for practice that are in the book. Okay, very good, very good. So let's switch to chapter number 4. Let's start sharing here. Okay, chapter number 4, we are going to take a look at reactions in solution. Now, the idea here is to understand why some reactions happen and also predict the products that are going to be formed in some very specific reactions. Last week, I already started talking about combustion. So here we are going to study some different types of reaction. Okay, so I will start talking about acid-base reactions. We will move on to precipitation reactions, then oxidation reduction reactions, and I will finish the chapter talking about electrolytes and non-electrolytes, and then the last part will involve determination of concentration of different solutions and also dilution. Okay, so to start this chapter, I would like to talk about two introductory tales here. First one is regarding tomato sauce. Some cookers experience in making tomato sauce. They usually add sugar to break sort of acidity of tomato sauce. Sugar will only mask the acidity of tomato sauce. A good cooker will add a little bit of baking soda, which is sodium bicarbonate, to the tomato sauce to break up the acidity of the tomato sauce. Okay, so we will try to understand why sodium bicarbonate is successful to achieve that. And the second case here that I would like to tell you is the case of the Palace 2. It was a building in Rio de Janeiro, Brazil. So that is a very interesting story. To make a concrete, you basically need four ingredients: fine aggregate, cement, coarse aggregate, and water. Okay, so important thing here regarding the water, it needs to be kind of a sweet water, okay, not water from the sea. So what those people thought about is, well, Rio de Janeiro is right here on the coast. Look, there is a lot of water and it is for free because it's from the sea. So they used uh, seawater to make the concrete instead of a pure water. The problem with the seawater is the huge amount of salt, and the salt that was in the concrete that speeded up the oxidation of iron in the structure of the building. And I think after 10 years, that created a hollow structure in the building. And the result of that was that the building collapsed. Okay, so we will try to understand why the salts in the water speeded up the corrosion of the iron in the structure. Okay, so let's start with acid-base reactions. So let's go back here a little bit. I showed you the different classes of compounds. We can have two major classes: ionic compounds, where one element loses electrons and another element gains electrons, forming a very stable compound. And the second class is called covalent compounds, where both elements need to gain electrons. Therefore, the idea here is that they will share electrons to achieve stability. I already showed you the acids, which are covalent compounds. And remember that we have two classes here: hydroacids and oxoacids. And today I would like to introduce you a new ionic compound called bases. All right, so let's start talking about bases. Just a second. Okay, so let me go forward here a little bit. Let's first start talking about the definition of a base. So base, by definition, is any substance that in water solution is slippery to the touch and has a bitter taste. For example, here you have here a cashew. So that's the part of the cashew that's very common, the cashew nuts. However, there is this whole other part of the cashew. If I'm not wrong, this is the fruit and this is the pseudo fruit. People from biology can correct me if I'm not wrong. Okay, so cashew, if you bite the cashew, it will have a very, very bitter taste because the compound here, the major compound, is a base by definition. The general formula of a base oops, is always a metal combined with OH. Okay, because bases are ionic compounds, they are composed by a metal with a plus charge and OH, which is always 1 minus. And this OH part of the base is called hydroxyl. Okay, so always a metal combined with a hydroxyl ion. Remember that the hydroxyl ion is always 1 minus. Okay, how do you name a base? Super simple. The first word is the name of the first element in the formula. Then you are going to give a space, and the second word is hydroxide. Okay, very simple. First word is the name of the first element in the formula, and the second word is hydroxide. For bases, do not use the prefixes monodiet, tri, and etc. to indicate the amounts because this is an ionic compound. Okay, so let's cover here 3 examples. First one is the NaOH. Second one is CaOH2. And the third one, NH4OH. Let me quickly switch to my other screen here, then I can write. Okay, so let's tackle those examples here. So always remember that the OH part of the base is always 1 minus, okay? So this hydroxyl part of the base is only capable of gaining 1 electron. And that's going to be combined with a metal with a Y plus charge to produce the base. Okay, so always here metal OH. So let's name the first one. So always look at the first element, which is the first thing before the OH. In this case, the first element is sodium. Give it a space, and then you are going to simply use the word hydroxide. Okay, NaOH, sodium space hydroxide. Let's look the second case. First element is always the element that is not the OH part of the base. So in this case is calcium. And very simple, guys. Give it a space. And the next word will be hydroxide. Okay. CaOH2 is calcium hydroxide. Why in this case I have CaOH2? Because calcium belongs to the group 2, therefore it is 2 plus. That's going to combine with hydroxide, which is always 1 minus. So therefore, each hydroxide can only get 1 electron, but calcium has to donate 2. When they combine, we need 2 hydroxides for each calcium. Okay, so we are always going to put OH in between parentheses, and the crossing will give the index outside of the parentheses. That indicates we have 2 hydroxyl groups for each calcium. Okay, third case here, that's a very special case. So what we have here is NH4. NH4 always has a plus charge, and this compound receives a special name, which is ammonium. Therefore, NH4OH, that's going to receive the name of ammonium space hydroxide. Okay, so every time we have that NH4 compound, the charge is always going to be 1 plus, and the name of that ion is ammonium. Okay, careful, don't mistake ammonium by ammonia. NH3, that's ammonia. NH4 plus ammonium. Okay, careful with the difference between these 2 compounds here. Okay, so I showed you that bases are substances that are usually slippery to the touch, and they have a bitter taste. Okay, those definitions are not very scientific, so we need a better definition for that. And I also showed you how to name bases. Okay, so let's get into a better definition of the base that is more scientific. A good definition for base is the Arrhenius definition. According to the Arrhenius definition of base, base is any substance that produces OH minus ions in water. Remember that OH minus is called hydroxyl ions. Okay, so let's see here, for example, sodium hydroxide. When we get pellets of sodium hydroxide and dissolve in the water, I'm going to indicate the dissolution process by placing the water over the arrow. What's going to happen here when we put the solid in the water is that the ionic bonding between sodium and hydroxyl will break, and that will produce the cation, sodium plus, and the anion hydroxyl. Okay, so always remember that OH minus is called hydroxyl ion. So that means the water is strong enough to break the ionic bonding between the metal and hydroxyl, that will split up this compound, and it will produce the cation and the anion, which is always hydroxyl. And the strength of a base is measured by how much OH minus is produced. More OH minus produced, stronger is the base. Okay, so that looks a little bit contradictory, because more the base is broken, stronger the base is. Okay, so before I start the definition of acids, I want to give one more example here, just to make sure we understand how what are the products formed when we dissolve a base in water. Okay, so let's see here, for example, the case of calcium hydroxide. We are going to dissolve that in water. So the dissolution process will be represented by water over the arrow. try to imagine that we have a calcium cation, and for each calcium cation, we have two hydroxyl anions. When we dissolve this compound in water, we are going to break the compound. So what we are actually doing is breaking the interaction between the cation and the anion, okay? So that will produce first the cation. Because calcium is from the group 2, the charge here is going to be 2 plus, and it's always going to produce the counterpart, which is hydroxyl ions. Okay, so pay attention here because we started with 2 hydroxyl ions that is represented by the index 2 here. Therefore, when we break the interactions, we must have 2 hydroxyl ions at the end, okay? So the index 2 here becomes the stoichiometric coefficient in the products, okay? So be very, very careful when we have more than one hydroxyl ion in the composition of the compound. Another strategy that you can use to figure out how many hydroxyl ions you are going to produce is to look at the net charges. Okay, calcium hydroxide has a net charge equals to 0. Once the interaction is broken, we have calcium here 2 plus. To balance the 2 positive charges, we need 2 negative charges, and each hydroxyl is only 1 negative charge. That's why we need the number 2 here, okay? The net charge at the beginning has to be equals to the net charge at the end. 2 plus will be neutralized by 2 minus. Okay, so I gave you the definition of bases in a very colloquial way, like relying on touch and tasting, and another definition that's more scientific, which is the Arrhenius definition. Okay? Any base in water will produce hydroxyl ions. Now let's move on to the definition of acids. Acids are any sour taste substance, which is not a scientific definition. The Arrhenius definition for acid is that acid is any substance that produces H plus ions in water. Okay, attention here. Acids in water will produce H plus ions. Let's see here, for example, HCl, hydrochloric acid. When we dissolve HCl in water, according to Arrhenius, the bond between hydrogen and chlorine will be broken, resulting in the production of H plus, and the counterpart here is going to be Cl minus. Okay, see here that the net charge at the beginning has to be equals to the net charge at the end. So this is a neutral compound. H plus is 1 plus, and Cl is 1 minus. Okay. So later on in the course, I'm going to show you that there is a single bond between hydrogen and chlorine, and the water is strong enough to break this bond and split this compound in H plus and Cl minus. The strength of an acid is measured by how much H plus is produced. More H plus produced, stronger is the acid. Some people like to write the water as a reagent in this reaction. So in this case, what's going to be produced is H3O plus and Cl minus, okay? So to keep the thing simple, let's use the simple way, just H plus is more than enough. We don't need to overcomplicate introducing the H3O plus ion. Okay, very good. So now we were introduced to a new class of compounds, the bases. We know how to name them. We know what happens when we dissolve a base in water. We have a very good scientific definition of a base. And we did the same thing for acids. We know what happens when we have an acid in water, and we have a good scientific definition for acids. Now what we are going to do is start to mix things and predict what is the product formed in the reaction. And we are going to start with acid-base reactions. So I don't have time to go over this topic today. Acid-base reactions is also called neutralization reactions because you are mixing an acid with a base, and that will always produce a salt and water. Okay, so acid-base reactions are a double displacement reaction. So on Wednesday, we are going to go over a lot of examples here, and the goal is to predict what is the product formed and to name the product formed. With that being said, I think that's good enough for today. I hope you have a good weekend, and I will see you tomorrow.
Have a good week.
Bye, George. Thank you.
Bye-bye.
Thank you.
Thank you. Have a nice rest of your day.
Bye-bye.